Hello everyone, I welcome you in my class. So in last class we have discussed the control system design criteria with a flight envelope. In today class we will discuss the longitudinal autopilot design. Okay. So in this lecture, before actually moving to the longitudinal autopilot design, first we will cover the actuator modeling. In actuator modeling, we will discuss the actuator dynamics, delay, and then how to model the delay using the per day approximation. Okay, because we have already know the aircraft dynamics, but dynamics is involved here also in the actuators, and when actuator will deflect based on the data which is sensed by the sensor, and sensor has some kind of delay. Okay, so that also we will discuss how to model the delay. And even the computation also some take time. So overall delay we will consider, because this is a very important part of a control system design. And then finally we will move to the longitudinal autopilot design. So pitch control loop already we have discussed and already we have implemented in the MATLAB and Simulink. Okay, but altitude loop as of now we have not seen. So in today class we will design the altitude hold loop. And if you remember correctly, the pitch control loop was designed based on second order transfer function. In that you have ignored the forward mode. But after covering the complete aircraft dynamics and we have linearized, then we have seen that there is a fourth order transfer function. If you convert the state space form into the transfer function model, and we see that there is a one mode is called short period mode, another mode is a forward mode. So fourth order transfer function you can replace with what we have designed in that class, and then you can move to the altitude hold loop design. So in actuator dynamics and delay modeling, the actuator dynamics can be considered as a first order and can be considered as a second order. So let's say we have considered the first order, and that means you are not taking account of any damping and all. Okay. So k divided by tau 1 s plus 1, you can take k is 0.1, generally in ideal case is 1 only k. You can take 0.9, 0.8 depending upon the characterization, and tau 1 is equal to 0.03. So that tau 1 is a time constant that decide how fast you are reaching to the what you have commanded. If you remember clearly, we have discussed this part. This is a time and this is the output, and this let's say is a 1, and you have a this response and this response, and the modeling transfer function is, let's say, k equal to tau s plus 1, where let's say k equal to 1 you have considered, and tau decides the response. That means if tau value is less, let's say this is a tau value 0.25 and this is tau value is 0.5 and this tau value is 0.8. Okay, so that means when you decrease tau, you will have a faster response by the actuator. Now the second thing is, this is all about the actuator dynamics, but the second, which is a very important part, is delay. Delay is a more important than other part. Right? For example, delay decides how robust your controller is. Delay directly affects the state margin, phase margin. And in this diagram, if I want to show the delay, that means, let's say, if I have commanded something, but by some time interval I am not getting any output, and after that I start getting output. So this part is known as a delay. So do not confuse with the actuator dynamics with the delay. Okay, you will see the delay in time axis. So who will be the responsible for the delay? One is the sensor. Sensor takes time to send the data to the actual flight controller. Let's say you have designed the flight controller, which is the math block. So this is a velocity sensor, pitot tube. It will take some time to send the data. There is one kind of delay. Another is computational delay. It will take some time to compute. If you sum up all the delay, then the question is what should be the value. So generally 40 millisecond, 80 millisecond is a standard delay which you have to consider in order to design the autopilot. And in a physical sense, you can have some feel for the delay. For example, like if I have deflected the elevator up, so by physics aircraft has to go up, right? But I have deflected, but aircraft has responded after some time, so it is dangerous, right? Okay, one example you can consider as a car you are driving. If you are taking the left turn, and by the time you have turned the steering left, but it is taking time to turn the left. Okay, if you take and if you want to at that time if you want to take a right turn, but still the aircraft the car is going in a left only, so it is wrong, right? So that means you want, when you deflect something and when you turn something, you want immediate response, right? But due to delay it is not happening. Okay, so delay is a very important part. So the question is, how will you model when you design the control system? So you can use a pod A approximation to model. So you can use pod A first order and pod A second order, but the practical results shows that pod A second order approximation is good. So like e to the power minus td into s. Okay, td is a time delay. Okay, so what is the expression of e to the power x? If I consider e to the power x, what is the value? 1 plus x square by factorial 2 plus s cube by factorial 3 plus dot dot dot, right? So if I put minus, it will become x to the power minus x, 1 minus x plus x square by factorial 2 or minus s cube divided by factorial 3, right? So I said already I am interested to take up to a second order, so that means I will neglect this part. Okay, so e to the power minus x will be 1 minus x plus x square by factorial 2. So how will you model e to the power minus td into s? What you can write? Actually, you can write e to the power minus td into s divided by e to the power td into s, right? By 2. That will become this. Okay, so if you expand this part, you will have a 1 minus tds by 2 plus tds by 2 divided by factorial 3. This is factorial 1 and tds by 2 whole square divided by factorial 2, right? And 1 plus tds by factorial 1, tds by 2 factorial 1 plus t into ds divided by 2 whole square divided by factorial 2. Okay, so what you can write? tds by 2 plus td square s square, and this is factorial 2 is 6 and 6, this is 2, right? And what is this? This is 4 and this you can write 8, right? And this what you can write? 1 plus tds divided by 2 plus t into ds square by 8. Then if you put the td value, you will get the approximated value. And there is a one more second order part approximation where you can write STD equal to 1 minus TDS by 2 and then TD square by S square, and then instead of 8 you write 12. TD is a time delay. So if you put the TD value 0.08 in this expression, you will get this value. So now you have a approximated delay. So now we have modeled the actuator dynamics and then delay also. So this is a typical view of a altitude hold loop. Please do not confuse each and every control loop with step by step. I will explain. So first thing is plant. So first you take Q by daily transfer function. So we have discussed the second order transfer function and we also discussed the fourth order transfer function. So first you take the plant, okay, and let's say this is a plant, okay. So now you have to have a actuator, like in this case longitudinal case elevator. So this is the actuator dynamics, and this flight computer needs a signal, sensor signal, that kind of delay, computer delay, sensor delay. So you have modeled the delay, okay. So this part, elevator or actuator dynamics, Q by daily transfer function, sensor, this is a plant with a hardware lumped model. That means you have included the actuator dynamics delay with a plant. So you can also complete, you can also say this is a real plant, you can say, okay. When I say longitudinal control, that means what? You have only two controls, two actuators. One is elevator and another is a thrust. Here the thrust is this. So by changing the throttle setting inside the cockpit, you can vary the thrust, and by changing the stick position, you can move the elevator. Two controls, right? So in two controllers, you have to execute the longitudinal flight. For example, let's say you are taxiing in a runway, then climb, take off rotation and climbing, and then cruise, and then descend, and finally land. So you have to use these two controllers in a very smart way in order to complete the flight. But the use is different for a climb and the use is different for a cruise. So in a for example, like in a takeoff, what you will do, you will put the thrust to maximum, and then you will wait to for a one speed to reach. Once it is reached to the takeoff speed, you will start, you will immediate deflect the elevator up in order to rotate the aircraft. Once it is in a climb, then you have to set the one particular setting, and by changing the elevator, you can actually move the pitch, and by regulating the pitch, actually you can control the speed. And once you attain the cruise flight, that means velocity is controlled by thrust and pitch is controlled by what? Elevator. So you can see the use of elevator and throttle is different in climb, and the use of elevator and throttle is different in a cruise. So we have a major three control loop in a longitudinal phase. First is altitude hold loop, today we will discuss, and then we will use the we will discuss the velocity control using command and pitch, and then we will discuss the speed hold control using throttle, okay. So now first we will discuss the cruise flight. So this part is clear, right? Okay. When you integrate 1 by s, you will get theta, right? Theta equal to q dot, approximated equation while design the controller. But in plant, you will not approximate, okay? You will take the feedback and you will use the PI controller, okay? So P loop is closed, and then when you multiply by V and divide by S, you will get H, and you will take the feedback and you can use the PI controller, you will get the altitude. So one by one loop I will try to explain you using this block diagram. So first what we will do, Q by daily, okay, transfer function fourth order. we will take the actuator, delay. Okay, so this complete represents the plant. So I am just saying this is a plant. Okay, plant. So when you integrate, you will get what? Theta, right? You will get theta. In order to ensure that your inner loop is working fine, what you will do? You will take a feedback and you will multiply by the KQ gain and you will close the loop. This is the first loop called rate loop. Once you have tuned this loop, then you will move to the theta loop. So this loop and theta loop already we discussed, right? This is minus, this is plus, and here you will use PI controller, right? And here the theta command will be given. Now when you multiply by this VA by S, and if you take the feedback, and here you will command H command. Okay, H command you are having, and here you will use PI controller. So please note that for a most inner loop, the command variable is given by this theta loop, and for this theta loop, the command variable is given by altitude loop. So let's say aircraft is flying and you have commanded altitude what? Let's say 1000 feet. So 1000 feet you have pilot has commanded. So that means accordingly theta will be generated. In order to attain the theta, Q command will be generated. And to attain that Q command, the elevator will be deflected. That is how it is happening here. So that is how you can attain the steady state level flight. So this gain is obtained based on root locus in order to ensure the proper damping. And then when you do next loop, in order to tune PI, you have a good response. Okay, if you satisfy the response less than overshoot 10%, setting time 5 seconds. Okay, if satisfied the requirement, you move to the altitude loop. So how many loops are there here? 3 loops, right? One is rate, attitude, and then altitude. Okay, and these are called filters. That means we'll discuss later in the class. Then sensor will give some data, right? That can be noisy. So you have to filter those signals, na? Depending upon the noise, high frequency signal or low frequency signal, or in between high and frequency. If you want to remove some kind of signal, then you have to use the filter, right? So that's why these are the filter. It is written. This is a filter. This is filter, and this is filter. And in between theta loop and H loop, I have enter this loop also. For example, like if some kind of gust is come, then you have to act very fast. That means you have to take account of H dot, how my altitude is changing in the. But the simple diagram is this. Simple diagram is this. Okay. So again I am saying, when you want to fly at a one particular altitude, pilot will give the command. Okay, and pilot will give the command, let's say 1000 feet. So you have to deflect the elevator in order to generate that rate. Okay, because if this is the command equal to 1000 feet, then accordingly at a one throttle setting, because this is a separate longitudinal controller, you have maintained one velocity. So that means in order to hold the altitude, you have to set a one theta. Okay, that is why theta has been commanded. In order to set one theta, you have to generate some pitch rate, and in order to generate the pitch rate, you have to deflect the elevator. That is how the loop is running. And do not confuse with the control and stability augmentation system. Stability augmentation system is this part, rate loop. That means continuously you are taking the feedback and you are trying to improve the damping. That means open loop damping was 0.3, but due to this rate you have reached to the 0.7. That means you have augmented something, right? So that is called stability augmentation system state loop. So the most important part is this part. In a inner loop we have discussed the root locus, right? So but was the ideal case. But have you noticed when you include delay, you will have a two zeros for a second order. You have a two zeros at a right half plane. So that means when you change the gain, the pole will try to move from left to right. What I said, if you increase the gain, what will happen? Open loop poles will move to the open loop zeros. So that is how this line is. See, this is without delay, right? One mod is short period, another one is a lightly damped fagot. These two. When you introduce delay, this is without delay. This you introduce the delay, this mod will try to shift towards the right half the plane. Because why? Because of delay. So as a control system designer, you have to be very sure that you should not cross this boundary, right half plane. Okay, otherwise system will be unstable. So that is why it is important to plot the root locus with delay and without delay. With delay, without delay, perfectly fine. Okay, everything is fine only. But once you introduce the delay, the pole will start shifting towards the right of the plane. Why? Because when you include the delay, there is a two zeros sitting in the right half plane which is trying to stress the pole. Theory I explained to you, right? That is important. Now, last class what we discussed? Bandwidth, right? So that means what is the bandwidth? When the in a Bode plot, when the magnitude is dropped by minus 3 dB or output is 30% reduction, that means at that frequency range is known as a bandwidth. That means here you are tracking perfectly well. Outputs and input are well tracked. You are commanding theta, getting theta. You are commanding altitude 1000 feet, you are getting 1000 feet. But at a high frequency, you have seen this drop. Okay. And already I have seen that there is a proper separation between the bandwidth of a inner loop and outer loop. So see, the bandwidth is how much? 0.7, right? And theta is what? 0.93. So which loop has a more bandwidth? Theta loop, right? And altitude has a less bandwidth. Why? Because inner loop has to act very fast. For a simple quad outer example, I try to explain you, right? Okay, let's say wind is coming from this direction. So what happened? Quad rotor will try to drag in this direction, but you want to maintain the same position, so you have to correct immediately. So that means inner loop should be very fast. Rate you have to generate very fast, roll rate, in order to counter that. That means inner loop should be very fast in order to hold the position. So that is why the two bandwidth separation should be very important. Okay, and you may ask how much it is. So you can take bandwidth separation 4 radian, 3 radian, 5 radian. Actually above 5 radian is good. So this is all about in this class. So we have covered the altitude hold loop. So in next class what we'll do, we'll try to cover the speed hold loop using throttle and velocity control using commanded pitch. Okay, and also you can see whatever so far control we have designed that correspond to the one trim particle condition. So the question is, how will you check the controller performance at that another trim condition, and how will you select those trim points? Okay, and as a overall picture of a control system designer, how will you comment on the controller performance on a different trim points, that we will discuss. Thank you so much.